Hello everyone, welcome back, and today we're looking at March 16th, paper 4-2, question number 6 of physics 9702. So the question number 6 says, a parallel beam of ultrasound is incident normally on the surface of a layer of fat of thickness 1.1 centimeter as shown in figure 6.1. For the ultrasound, I1 is the intensity just after entering the surface of the fat layer, I2 is the intensity incident on the fat muscle boundary, I3 is the intensity reflected from the fat muscle boundary, and I4 is the intensity received back at the surface of the fat layer. Some data for the fat are given in figure 6.2. They have given us a specific acoustic impedance, which is 1.4 into 10 raised to the power 6. Then we have the density, and then we have the absorption / attenuation coefficient. A part. Calculate the time interval between a short pulse of ultrasound initially entering the layer of fat and then returning back to the surface of the fat layer. So how do we do this? Okay, whenever you see a question about ultrasound, these are the three formula that you should immediately list down, because these are the three formula that are used in ultrasound calculations. One is specific acoustic impedance, that is Z is equals to P C, where this is rho actually there, which is the density, and C is the speed of sound in medium. And then you have the intensity reflection coefficient, that is IR over I naught, Z1 minus Z2 over Z1 plus Z2 whole square. Attenuation of ultrasound, which is I is equals to I naught e raised to the power minus mu x, where I naught is the original intensity. Now they want us, in the A part, they want us to find the time interval between a short pulse of ultrasound initially entering and then returning back. That is to say that if I have an ultrasound entering from here, this is for 1.1 centimeter. It travels all the way and then it comes back as well, because it says returning back to the surface. So what's the total distance that's covering? It goes 1.1, it then goes 1.1 back, so the total distance it travels is 2.2 centimeter. Now we know when we want to find time, we know what time is. Time is distance over speed. So we have the total distance, which is 1.1 plus 1.1, which is 2.2, and then you got to convert it into meters, which is 2.2 into 10 raised to the power minus 3. And then how do we find the speed? Now we know we can use this formula right here. We have the Z, we have the density, and since this is C is the speed, so we can find C from there. That's going to be the Z that is given to us in the question is 1.4 into 10 raised to the power 6. Density is given to us as 940, and we just have to find C from there. Now if you plug these values in the calculator, you have 1.4 into 10 raised to the power 6 divided by 940, and you get 1489.36 as my speed. And now when I divide this from the distance, that is you get 1.477 into 10 raised to the power minus 5, which you can also write as 1.5 into 10 raised to the power minus 5. And that was it for A part. Moving on towards the B part, that's it. Calculate the ratio I2 over I1. So when you see I1 and then you see I2, clearly you can see that I1 was the initial, and then I2 is when it has traveled a certain distance. So when it has traveled a certain distance through the muscle, it's going to lose some of its energy, so that's going to lead to attenuation. So which formula out of these three best fits? That's going to be the attenuation of ultrasound, because it isn't reflecting at all. It started off at I1, it ended up at I2. That means it has lost some of its energy. That's going to be attenuation. Then that's going to be I is equals to I naught e raised to the power minus mu x. I naught is the original intensity, which is I1 and this is I2 essentially. So I2 over I1 is just simply going to be equal to e raised to the power minus mu, which is the attenuation coefficient that has been given to us as 48, and x is the thickness, which is 1.1, and we're just going to write 0.011 because we need to convert 1.1 into meter. And then when you write this down, e raised to the power minus 48 into 0.011, and you get 0.59 as your answer. That's it for B part. Moving on towards the C part. Intensity I4 is 0.33% of intensity I1, which essentially is I4 is equals to 0.33 over 100, which is 0.0033 I1. So it's just literally giving us the ratio I4 over I1, 0.0033, and I'll let you know why do we need it in the first place. Determine the ratio I3 over I2. Now if you look at the figure 6.1, you're going to see how I1 is the initial intensity when the ultrasound entered the fat layer, and then I4 is the final intensity when it's leaving. So finding its ratio I4 over I1 is essentially saying that the ratio of the initial final over initial, and what is that going to be equal to? That is going to be equal to everything that happened to the ultrasound on its journey from I1 to I4. That is to say, in simple words, this I4 over I1, it's like final state over initial state. Think of it as like final state over initial state, and that is all going to be equal to everything that happened to ultrasound on its journey from I1 to I4. That is I2 over I1, and then I3 over I2, and then I4 over I3. So final minus final over initial is going to be equal to all the ratios, everything that happened to ultrasound on its journey from I1 to I4. So we have this ratio right here, that is 0.0033. I2 over I1 we just found in this B part, that is 0.59. I3 over I2 something we have to find, and then I4 over I3, again you can see that I3 traveled to I4. That means there was some loss in the energy. That means it's the attenuation of ultrasound. It's again going to be 0.59, and then when you plug these values in, 0.59 into 0.59, 0.0033 divided by answer, and you get 9.5 into 10 raised to the power minus 3 as your answer. And I'm just going to write this down here, and that's it for C part as well. Now moving on towards the D part. The specific acoustic impedance of the muscle is greater than that of the fat. State the effect, if any, on the value of the ratio I3 over I2 often increase in the difference between the specific acoustic impedance of the muscle and that of the fat. 1 mark. Okay. One thing you need to understand, the greater the difference between the specific acoustic impedances, the greater the reflection and very less transmission. So if there is a very big difference in the specific acoustic impedance, very less transmission and very great reflection. So what is the ratio I3 over I2? If you look back at the figure 6.1, you will see I3 over I2 is essentially the ratio of reflection, because I2 was the intensity of the ultrasound. It then hit the muscle and then it reflected back, and then its intensity converted into I3. So this is essentially deflection. So when the difference increases, so when we know that when the difference increases of the specific acoustic impedances, which they are saying in the question it does, the reflection is going to increase as well. And since the ratio I3 over I2 is the ratio of reflection, so we're going to say that this ratio increases because the specific acoustic impedances has a very large gap, due to which there's very less transmission and very great reflection. And that is it for question number 6.